So let now this is a vector space. This is a vector space of dimension 3. Sorry, dimension 9. Okay. Now what we define is the following. So let R be Earth. Now the collection of all, okay, we assume B is by which you mean that B is linear with respect to each of these arguments when the other two arguments are held fixed. That is, B is linear arguments when the other two okay. Now that is pretty clear what is happening. So when you keep x2 and x3 fixed, then this will become a function of x1 and it becomes a linear functional on R3 with x2, x3 fixed. Similarly, when x2 is allowed to vary, x1 and x3 are fixed, B is assumed to be linear with respect to x2. So also when x1 and x2 are held fixed, B is assumed to be linear with respect to x3. That is, we have the following: B of C1 Cx1 plus C prime x1 prime this is equal to C of B C prime of B x1 prime x3. Similarly, for the second argument and similar statements the second and arguments. Then we say B is 3 linear. Then we say B is 3 linear. That is the definition of 3 linear spaces. Now look at the collection of all 3 linear forms on R3. With usual addition and scalar multiplication, it becomes a vector space. So, let B all three linear on R3. Now, we define B1 plus B2 of and it's also CB where C belongs to R. Now, with this addition, so you see that if B1 and B2 are three linear forms on R3, then B1 plus B2 is a three linear form on R3. That is easy to verify. CB is a three linear form on R3 where C is a scalar and B is a three linear form with this definition. Now, that they are very easy to verify. Therefore, this becomes B is vector space of now we shall explore what is the dimension of this space. Okay. So, you naturally ask the question, what is the dimension of B? This is the question that we are exploring. Now, you see that the obvious way is to work out a basis for this space. But before that, we explore the following. That is, we start with a set of vectors in X. So, consider before that, what we do is we want to say something about this. Okay. Make an observation. In fact, we prove it. Okay. So, we prove that B is completely determined by its values on E1, E2, E3. Okay. So, before that we take, So consider that E1, E2, E1 forms a standard basis for R3. Therefore, now we look at the collection of vectors. So you defined by EK. One, two, three. That means you have got E1, 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 E2 or E1, E2, E1, E1, E3, E1, etc., etc. Okay. So how many such choices are there for each place? There are 3 choices. Therefore, there are 27 such vectors. Three to the power 3 elements are there. Now what we want to assert is that if we know the value of a given B at EI, EJ, EK for all IJK, then B is completely determined. Okay, so that's the first statement. B is, so you call this some name you can give this. So we already used here B, and therefore we will use some collection, say some collection Y. Okay. Right. So Y, see what we are trying to prove is this: Y forms a basis for, okay, no, that's not what we want. What we want to assert first is that given B, B belonging to B, B is completely determined by the values it takes at each of these vectors in Y. So B is completely determined by the values B takes EI, EJ, EK, this collection for so this the value B takes on this 27 vectors completely determines B. Now this is quite easy to prove, because what we know is that, now note that B belonging to B linear, 3 linear. Therefore, we compute what is B x1 x3 is equal to B at you can say x11 E1, x12 E2, x13 E3, comma x21 E1 plus x22 E2 plus x23 E3, comma x31 E1, x32 E2, x33 E3, where R3 and hence have unique representation given by xi equal to xi1 E1 plus xi2 E2 xi3 E3 for I equal to 1, 2, 3. The scalars are uniquely determined. Okay, so xij's are scalars. Therefore, you know that each vector is now uniquely represented by this. Now, what we apply is use the fact that B is 3 linear. Okay, recall the definition of 3 linearity, and then if you make the computation, you get B of this is equal to the following. Sigma I equal to 1, 2, 3, sigma j equal to 1, 2, 3, sigma k equal to 1, 2, 3. The elements that the coefficients that gets pulled out is this B I1 B1I, sorry, X1I X1I X2J X3K B at EI EJ EK. Okay. Therefore, there are 27 terms in the sum, and the coefficients come out from here. Okay. So this is something that can be easily verified. So it is left for quick verification, and actually the tree linearity plays the role, because at each stage you have to work with it and then find out what it is. Okay. So expand the whole thing using tree linearity, then you will end up with this. Okay. So that shows one thing. B, we have started with an arbitrary element of script B, and its evaluation at any x1, x2, x3 is completely determined by its evaluation at EI, EJ, EK for all choice of I, J and K, because each of the xi's have a unique representation in terms of E1, E2, E3. Okay. So one can get this. Now this is a very important step. Okay. Therefore, we can work backwards and say that if you prescribe a scalar valued function at EI, EJ, EK, that is at these 27 points, and then extend it with tree linearity, then you end up with a tree linear form on R3. Okay. Right. So one can, by prescribing this and extending and allowing to extend this over the whole space using this formula, one gets a tree linear form defined on R3. So let us work it out. So we will now construct some specific tree linear forms. Write it out. Okay. Therefore, the values EI, EJ, EK that means at 27 points, if you fix the values of B, then a unique a tree linear form is defined. That is the important part. So we shall use this result. Now we use this fact to define certain n-linear forms. Definition. Define this is the notation EK this is a tensor product EK by what you have to do, you have to fix it at the 27 points by setting EL, EJ, EL, yeah, what's it? EL equal to delta J this means that at EL, EM, EN, okay, only EL cross EM cross EN is 1, all others are 0. Okay, so that's easy to check because you have to have 1 here. So L is equal to I is equal to L, J equal to M, K equal to N. Okay, at all other places, at all other points, EI, EJ, EK is 0. So remark equal to 1 and is 0 takes the value 0 at all other points. Okay, now extend using 3 linearity to the whole space X, which is R3 direct sum, R3 direct sum, R3 direct. Okay. Then, and let us denote this extension by EI tensor product EJ tensor product EK, right? So we have now 27 3 linear functionals defined on R3. Thus we have three linear forms. When you say R3, it is actually you are defining a scalar map on R3, direct sum R3, direct sum R3. That is the meaning of that. Okay. Now, what is the utility of this? So, first of all, our expectation is that even from our experience of working on R2, our expectation is that this forms a basis for the space B. Okay, so that's the next theorem. So theorem basis for B. Basis for okay. So what do we have to do? We have to do two things. One, verify that this collection is linearly independent and show that every three linear form can be written as a linear combination of these forms. Okay, so let us do that. So first parts of proof. Equal to 0. So you know that these are all each one of this is a three linear form. So their linear combination is also a three linear form. Now we are assuming that this three linear form is equal to 0. That means its action on every point Ei, Ej, Ek is 0. Okay. Observe that we are assuming and taking it as and is set to be 0. 0, that is the 0 element of B. That means it's a three linear form which takes which vanishes at every point in R3 cross R3 cross R3. I mean R3 direct sum, R3 direct sum, R3. Okay, right. So now one easily observes that. So if we denote by C define EK one, two, three. Then C equal to 0 implies C at EL, EM for every choice of element. That is belonging to that's the meaning. So its evaluation at every EL, EM, EN is equal to 0. Now we observe the following, that C, which implies C at EI, EJ 0. What does it mean? But you can easily compute what it is. C at EI, EJ, EK is essentially using the definition of EI, EJ, EK. So Ci this is equal to, now this is true by if you vary I, J and K, then this is true for every choice of I, J and K. So there is nothing to prove there, which implies since C equal to 0, this is equal to 0, you get Cij that implies the collection is linearly independent. Okay. Now let us show that every B belonging to B can be written as a linear combination of this. Okay, of say these 27 elements. Now what is spanning property? So what do we do? So we define B prime or B tilde to be equal to okay, what we do is so let then B defined for all Pk this is defined because you know that it completely fixes B also. This completely determines B. Let B be okay. Let B tilde defined by defined by Ek I then what you have B tilde at EL is equal to what? Now you apply this and then use the property or how EI, EJ, EK is defined, then this is equal to B, EL, EM, EN. What does this mean? This means that B and B tilde are identical on EI, EJ, EK. Okay? Therefore, if you start with any B can be written as a linear combination of this. Therefore, B equal to B tilde. Okay, which implies B is a linear combination of linear combination of That means this collection spans these. That is, this collection. What did we denote this collection? This collection we had given a name, that is Y. Forms a basis for so the dimension of, so that in turn implies so you have a 20 this is a 27 dimensional linear space over R. The set of all 3 linear forms on R3 forms a 27 dimensional linear space over R3. Okay, so that's the basic thing. Now what we want is, we want to go to alternating 3 linear forms, and I am not going to define it this time, but I will do it in my next lecture. Okay, but before that, let me just rework the notation so that I can push it across to the general case very easily. So let tau be a map from be a function. That means tau 1 is equal to one of the 3, tau 2 is one of the 3, tau 3 is one of the 3. So that means tau I there is no restriction, it is a function. That means for each I there is a unique element from 1 to 3 associated with it. That is the only thing. So we are considering all functions defined on the set 1, 2, 3. Okay, right? There are 27 elements. Let F denote now what I want to do is I want to rewrite B we have written as a linear combination of this. Okay, so we want to rewrite B in this notation using tau. Okay. So given B, B can be now written as summation over all tau belonging to F. Okay, write it this way, that is B at tau 3 this is the new notation that we have. Okay, or simply write, if we write equal to B tau this is the representation for B. It's a very handy representation. We shall need this while generalizing it. Okay, so that's about it. Now what we are looking for is the following. Okay, so let me just make the following statements. We now look at what are called alternating when do you say something is alternating? A three-linear form is alternating if any interchange of its parameters will change the sign of B. So that means B is alternating if B of minus B of Ej, Ei, Ek. That is one change. Now once again you change here. So this is also equal to minus of B Ek Ei. That means we have interchanged these two. Then this is also equal to minus of this. Now this is also equal to minus of B of Ei Ej. Okay, so we have interchanged this pair and this pair. Okay, then these are the properties that it should satisfy. Okay, or more generally we should write this. This is not the definition. I mean, I think I would rewrite the whole thing as follows, that B of Xi, Xk equal to minus b of xj, xi, xk. This is also equal to minus of b of xi, xk, xj. This is also equal to minus of xk, xj, xi. Okay. This is what you mean by alternating. That means interchange of any pair of arguments will, keeping the third one fixed, will change the sign. Okay. So that defines it. Okay. So it is not an arbitrary three linear form, but a three linear form with a restriction. Now it's quite easy to show that the collection of all alternating three linear forms form a vector space. It's easily seen that this is 2. The collection of all alternating let us denote it by A. Script A. Okay. So script A now the question is, what is the dimension of script A? That is a vector space, then it has a dimension. Okay, right? What is fascinating is that we can prove that is one dimensional. Now this is what we want to prove, and that in turn will help us to define or determine a structural property of the determinant of a matrix. We shall come to that again, and we have now said this notation is quite useful because we shall use it later, okay, when we generalize it. Once you fix this notation, then you have a lot of leverage, okay, because you can write everything briefly, or rather you can have a lot of brevity in the expressions, And so we will explore this further in our next lecture. Thank you very much.